Okay, this is number 15 and 7.3. And what that says is we want to revolve this region, and the region is bounded by the line y equals x, that's this diagonal line here. Y equals 1, that's this horizontal line. And then x equals 0, and that's a vertical line, which is actually the y-axis. And we're going to revolve that around the x-axis. So I drew my sketch of my region, so this is the region that's going to be revolved around. Now in here we're going to have kind of a hole. This is why we're going to use the washer method. Now right at this point we won't, but from there on we'll have little gaps here. So the first thing I can do is I can draw my reflection, or after I revolve it about 180 degrees, it's going to look like this. And you can see how it's going to go around. And what we're going to, basically it's the idea we're going to have this large cylinder, and out of it we're going to kind of cut out this cone. So I think you can kind of see the cone there. There's the cone, and this whole thing is the cylinder, so we're going to take this cylinder and we're going to cut out the cone, or subtract. So we're going to take the whole thing and subtract the inside part, the cylinder, and then we should get the volume of what's left. So it'd be kind of like a bowl with a kind of a cone type interior. So if we look at this, this would be like the top curve, and this would be the bottom curve. And we'll just follow this radius, and this would be the big radius, the outside radius, and this is the inside radius. Okay. And so we're going to take the whole thing, which is this area, times this distance from 0 to 1. And they do intersect at 1, when y equals 1 and x equals y, that's the point 1, 1, so that's the intersection point. That's kind of from the graph, you can figure that out. So we're going to integrate this from 0 to 1. And we're going to take the whole thing, which is a cylinder, and then we're going to subtract the cone. That's what this part would be. And remember, it changes, the radius changes because it's based upon this bottom curve. So there's your sketch. So volume equals the integral from 0 to 1. Again, that's where they intersect, so that should be easy to figure out. And we can take the pi out, so I should remove the pi. That makes it a little bit easier. And I'll have I guess r squared minus little r squared dx, and then we'll substitute it in. So volume equals pi times the integral from 0 to 1. And my big R squared, that's a constant, that's just y equals 1. So that goes there. Minus little r squared, and that's just going to be y equals x, or x equals y, y equals x. That's squared, pardon me. And that's dx. So again, this is the top curve, which is the line y equals 1, and the bottom curve, and that was the y equals x. That's all there is to it. So volume equals pi, and we can simplify this a little bit from 0 to 1. 1 squared is 1 minus x squared dx, and we're ready to take our antiderivatives. So volume equals pi, and we'll evaluate this from 0 to 1. And 1 squared is, the antiderivative of 1 is x, and the antiderivative of x squared is x cubed over 3, evaluated from 0 to 1. We kind of luck out because our 0 is going to just drop out, because 0 minus 0 cubed over 3 is just 0. That's going to be pi times, if I put 1 in here, I get 1 minus 1/3, and 1 minus 1/3 is 2/3, so just 2/3 pi. That's all there is to it. So not bad. Try to make yourself a good sketch. Spend a little bit of time. You can do it. Think about it. Kind of just copy this pattern if you want, but just try to see if you can sketch these things, because it's kind of nice to have a good sketch that kind of illustrates what's going on.